Hello and welcome once again to the lecture series for computer graphics. We've already dealt with lecture 1 through to 3. Today we are going to talk about lecture 4, which is centered on scan convention. So before I proceed, I will talk about the definition of what scan convention is, and the essence of having some sort of algorithm just to help us use scan convention or make scan convention effective. Now, when we talk about scan convention, by definition, it is a process of representing continuous graphic objects as a collection of discrete pixels. So, a typical example would be a line is defined basically by its 2 points or 2 endpoints, and its line equation. So, when you have a line, it's begin point and an end point. Once you have the line equation, you will be able to come out with the intermediate points that is needed to create a line. But in considering circles as an example, we also would need a circle. By its definition will be to have its radius and also a circle equation. So a circle is defined by its radius and the center position, the circle equation. Now, there are advantages of developing algorithms for scan convention, and these are the 3 main advantages of developing algorithms. The first one is centered on the generation of graphics or the generation of graphic objects at a faster rate. So when you have an algorithm created, it's very easy to generate a graphic object as fast as possible. The second reason why we will need to have an algorithm for scan convention is most of the algorithms that are being used have memory that can be used efficiently. So using algorithms, memory can be used efficiently in coming out with scan convention. The other one is also centered on the fact that algorithm can develop a high level of graphical objects. So when you use an algorithm, you can also have the chance of getting a very high level graphical objects created. Now, there are examples of objects that can be scan converted. So an example can be a point, line, sector, arc, polygons, rectangle, and the special characters or characters that we have. You should bear in mind that the definition for scan convention, as we said, is the process of representing continuous graphic objects as a collection of discrete pixels. So you have a continuous graphic object being brought in the form of discrete pixels. So once you have an object in a 3D world, by the use of scan convention, you can bring out the pixels out of the continuous graphic object. Now, the process of doing this conversion, or the process of converting the graphic object to its discrete pixels, is what we term as rasterization. Most of the algorithms that are being implemented varies from one computer system to another computer system. An algorithm working for maybe Windows might be a little different from an algorithm that would work with the Linux environment. Now, when we say a pixel, we've already talked about it in previous lectures. The term pixel is a short form for picture element. So it's also called a point or a dot. Now, basically, it's also the smallest picture unit, which is accepted by most of the displayed units that we have. And mind you, we've already talked about display devices. An example might be the monitor. So the monitor has been structured in such a way that it would accept the smallest picture unit, which is what we call as a pixel. So a picture is most of the time constructed from thousands of such pixels. So we have lots of pixels coming together to form a picture. And most of the pixels are generated using commands. Now, when we take a closer look at what I'll be showing you in the next slide, you will realize that the closer the dots or the pixels are, the better the quality of the picture. So if you have most of the pixel dots or the points coming together, you would have very good quality of picture that will be introduced or displayed on the screen. So the closer the dots are, again, the crisper the picture would be. And you should also bear in mind that picture will not appear jagged and unclear if the pixels are closely spaced. Once we have the pixels closely spaced, you will never have the picture being jacked up or unclear. Now, you should also know that the quality of a picture generally is directly proportional to the density of the pixel on the screen. So if we have a very good picture, then it's very likely that we have a lot of pixels coming together to form this quality. So a 1080p monitor, that tells you that the kind of picture or graphic object that is being displayed with this type of display unit or video unit has very high resolution or have very high density of pixels. So you have lots of pixels coming together to be able to display an image or an object in this particular screen. Now, a pixel is also termed as a pearl. Now, pixels are also defined as the smallest addressable unit or element of the screen. So each pixel has some sort of intensity value, which is represented in memory of the computer. So anytime you have the pixels that are being displayed on the screen, each one of them would have an intensity value. If the intensity is high, that is when it's going to display more. If it has a low intensity, then maybe that portion of the picture or graphic that is supposed to be displayed is turned low for viewers to see. Now, once each pixel has some sort of intensity value, which is represented in memory of a computer, we will term this as the frame buffer. So the frame buffer is also called the refresh buffer. This memory is a storage area for storing pixel values, using which pictures are displayed. So the frame buffer can also be referred to as a digital memory. Now, inside the frame buffer, image is stored as a pattern of binary digits, either zeros or 1. So there is an array of 0 or 1 used to represent the picture. So for a black and white monitor, the black pixels are represented using 1s, and the white pixels are also represented using 0s. In the case of a system having 1 bit per pixel frame buffer, this type of system is termed as a bitmap. So in systems where multiple bits per pixel is used, we call it as a pixmap. It's a pixmap, P-I-X-M-A-P, as a pixmap. So there are some algorithms that are available to help in scan conversion, and we'll talk about each one of them in the next slide. But before I go on, you should bear in mind that from the diagram as you see here, let me activate the laser pointer. From the diagram as you see over here, so each pixel has some intensity value which is represented in memory. and this memory is termed as the frame buffer as I was talking about. And this same frame buffer is also called the refresh buffer. Now looking at this one, you can see this is a pixel which is displayed on a displayed unit, and each of these boxes will represent a pixel. So to know the location of a pixel, it also has some sort of an address. So looking at this one in the XY plane, you can see this pixel is on the row on the fifth X, or the sixth value or fifth value of X, and also on the fifth of Y. So the address for this particular pixel is what we have here as 5, 5. So 5 the X coordinates and the 5 for the Y coordinates are shown here. Now let's go to the other type of, or the types of scan conversion algorithms that are available. I'll be using the digitizer and the light pen. Okay, right, so the first scan conversion method or algorithm that we're going to talk about is the DDA, as you have here, DDA, and it stands for Digital Differential Analyzer. Now, what is this whole thing about this Digital Differential Analyzer? First of all, an algorithm which is actually used for drawing lines. We call it a scan conversion method. So it is a scan conversion method for drawing lines. That's the first thing that you should know. It's a line drawing algorithm which is used for it's a line drawing algorithm, and we call it the scan conversion method. So the scan conversion method, the digital differential analyzer, is a scan conversion method for drawing lines. And this algorithm or this method also uses the incremental approach. So it uses the incremental approach. Alright, so what do I mean by it's using an incremental approach? Let's take a line segment where we have starting points of the line, maybe A, the ending point somewhere here. So by saying that it uses the incremental approach, what we mean to say is by taking the previous point, the new point is drawn. So from here, this is the beginning point. So by taking this previous point, a new point, pixel, is drawn. So all these points will be drawn based on the previous points to arrive at point B. So by taking this previous point, this new point is drawn. By taking this previous new point, this pixel or this point is drawn. Likewise, this, that, and the rest. So if you want to draw a line, use all the points forming the line. So in the drawing of the line, we will use all the intermediate points. All these would have to come together to be able to draw the line from point A and to point B. Okay, so the third point is the difference in the pixel points is to be analyzed. It needs to be analyzed to be able to draw the line. So let's take an example, like let's take the XY Cartesian coordinates plane. So we have an XY plane, we have our Y here, and of course this is the origin. Now let's draw any line segment. Now you know, to draw a line, we would always have a beginning point and an ending point. And within these 2 points, the beginning and the ending, we will you get what we call the intermediate points or pixels. So these are all pixels. These are all pixels that falls within the point A or pixel A and pixel B. So now the difference in each pixel needs to be analyzed to be able to help us draw the straight line. So we have the difference between this pixel and this pixel needs to be analyzed. This pixel and this pixel also needs to be analyzed. And when that is done, then we will be able to create the line segments fully using this algorithm. So we say it is an incremental approach mainly because it performs the computation at each step and uses the outcome of the previous step. So to get this one, we need to compute to find the difference between the difference in pixel points of these ones, do the computation before this points, the new intermediate points will be can be drawn using this algorithm. Now, this is just an introductory to the DDA or the Digital Differential Analyzer algorithm. So in the next step, I'm going to explain the algorithm itself, and when that is done, then we'll go through some few examples, about 2 examples, so you get familiar with how the system works. So whenever you think of the DDA, the first thing that should come in mind is it's a line drawing algorithm. So we need to know some properties of a line to be able to use this algorithm as effective as possible. So a straight line equation is of the form as you can see here. Y is equal to mx plus b. Now let's take the xy plane as you can see over here. So from this point we have point A, which is represented by the coordinates x1, y1, and point B also represented by the point x2, y2. Now, and of course here is the origin of the Cartesian plane, xy plane. Now the straight line equation is of the form y equals mx plus b. So if the line has 2 endpoints, which is A and B, with these coordinates, then the slope of the line is given by this formula: the difference in the y value and also the difference in by the difference in the x value. So y2 minus y1 over x2 minus x1 will give us what we call the slope. And the slope is also termed as the gradient. So m is equal to m, which is over here. M is equal to y2 minus y1 over x2 minus x1. So this equation, the difference in the y and that of the x is what we have over here as the slope, m over here. Now when the line crosses the y-axis, so for instance, if the line crosses the y-axis at maybe 2, then we will say the y-intercept is 2. If it crosses the x-axis at maybe negative 2, then we also will say the x-intercept is negative 2. Now from the equation of the line, y equals mx plus b, b as we see here is what is termed as the y-intercept. So from here, we already know that the difference in y but the difference in x can also be represented as change in y over change in x, which can also be represented in the form as dy dx. Now, the equation of a line can be created or can be generated in 3 main ways. The first one is y equals mx plus b, which we already have talked about. The second way of writing an equation of a line is represented in this form: y minus y1 is equal to y2 minus y1 over x2 minus x1 all into brackets x minus x1. So this is the second way of representing an equation of a line. The third and final one is represented this way as x over a, its intercepts, plus y over e, which is its intercepts, is equal to 1. So why are we really talking about the equation of a line and all of that, and how does the algorithm fit in this? Now you should bear in mind that the DDA algorithm, as we've been talking about, is based on the calculation of the change in x and also the change in y. So the calculation of these two are very important when we think about using the digital differential analyzer. So once we have that in mind, let's go to the next point. So from here, we already know of the equation which states that y equals mx plus b. So from this angle, we see the change in y is represented by m, which is the gradient, times the change in x from the equation m is equal to change in y over change in x. So making change in y the subject, we'll have m times x, giving us equation 1. In the same vein, making x the subject, would have change in y over m, which is the gradient. Now, with a given line, the slope can be of any form in terms of it being positive or negative. Now, what does it mean to have a slope being positive or negative? So when we have m greater than 0, of course, then it means the slope, which is the gradient, is positive. When we have the m less than 0, it means the slope is negative. If the value of the slope or m is positive, then the change in x and the change in y values are increased. So it means the values of x and the values of y coordinates will be increased, else it will decrease. So there are three main scenarios that we can find when we talk about the slope. So the first scenario, or the first case, is when we have the gradient being less than 1. So by definition, the gradient is represented as m is equal to the change of y, change in y over change in x. So if m is less than 1, then what we mean to say is, assuming the change in the y coordinates is, let's say, 2, and the change in the x coordinates is, let's say, 5. So then the value, what we would get over here will be 0.4, which is less than. So in this case, m will be less than 1. So by saying this, we mean to say that the change in, whenever we have the change in y value to be less than the change in the x value, then we will always would get a gradient which is less than 1. So in the same way, in the Cartesian plane, when we have a line, you can see that the change in y value over here, change in y value, and that's of the change in x value, would have the change in y value being less than the change in x value. So in other words, the change in y value will be small, the change in the x value will be more than that of the y value. Hence, we will have the slope being less than 0. Looking at the we'll have the slope being less than 1 over here. So when we have a situation where the slope is less than 1, then the xn, where n is the new intermediate points, these are, we need to form the line from A to B, we will need all these intermediate points. So when the slope is less than 1, then it means in the calculation of the intermediate points, xn, which is the new coordinate for x, will be equal to x1, which is, so if you are picking out this one, so the new point, to calculate this new point, you will need x1 for this one, and we'll add 1s to it. That will give us the new x coordinates for this one. And its y coordinates will also be y1, that is a y1 for this a, if a is x1, y1. So it will be y1 for this a point or pixel, plus the coordinates, plus the points or the gradient that we have created. So in a case where m is less than 0, this is the formula that you need to have in mind to be able to create the new point, which is xn, or intermediate points on the line. Now let's look at the second case. If m is greater than 1, so still using the same formula, the gradient is change in y over change in x. If m is greater than 1, then it means the change in y is of a big value, and the change in x is a small value. So assuming the change in y is of value 5, the change x gives us a value of maybe 3. So this tells us that you have a value which is greater than 1. It should be probably 1.667, and this m value obviously is greater than 1. So when we have a situation like this, then the new coordinate, the new point that will be created on the coordinates, new points, these points that needs to be created. So the x coordinates, the new value will be x1 of the starting point plus 1 over the gradients. That will give us the s coordinates of the intermediate points right after the starting point of the straight line. And its y new value for the intermediates will be y1 plus 1. So for the next case, when we have the gradients to be equal to 1, then it means the change in y value over the change in x value is the same. So if we have the change in y value to be 5 and the change in x value to also be 5, then of course gradient will be equal to 1. So in a situation like that, we'll just add 1 to the intermediate point. So we have x of the new coordinate, the x1 of the previous coordinate plus 1, and the y of the new coordinate will be x1, which is y1, which is a new coordinate, the old coordinate plus 1. So these are the three scenarios that we can find when we talk about DDA algorithm. So these are the three things that you should have in mind. So once we have these formulas in mind, we should be able to use the DDA algorithm to tell or come out with the intermediate coordinates that are needed to form a straight line when we have the points A, B already given us. So we should be able to use this algorithm to be able to come out with these intermediate pixels or points. All right. So now let's go on to how the algorithm really works. Now this is how the DDA algorithm looks like. I start from step 1 through to 9. From what is shown in the algorithm, first of all, we've discussed about the cases, the three types of cases that are available when you're thinking about the DDA algorithm. So the first one was when m is less than 1. We had the xn, the s coordinate for the new intermediate point or floating point to be represented this way, and that of the y also represented this way. That is for case 1. And for case 2, we had a situation where m is greater than 1. So we'll have our xn being equal to x1 plus 1 over m, and xyn also being equal to y1 plus 1. And finally, third case where we have the gradient being equal to 0. So in that situation, in that case, we have xn being equal to x plus 1, and also its y coordinates being equal to y plus 1. So with these three cases in mind, this tells us that before we can even use this algorithm, first of all, we need to create a line. First of all, we'll be given a point or 2 points, maybe points A and B. I've been using A and B all the time. We will be given 2 points, and we need to create these intermediate floating points to be able to create a line using this algorithm. The first thing that we need to have in mind is the coordinate that have been given. Coordinate for A1 might be x1, y1, and that for B1 might be x2, y2. Let me just write it correctly. We have x2, y2. Yeah, so when we have this in mind, the first thing is we'll be given the 2 coordinates, and we'll be told to find out the intermediate floating points that will help us come out with a straight line, to be able to draw a straight line. So in the algorithm, the first step is to accept the start and end point coordinates, which is x1 and x1 y1 and x2 y2. Now the next is to calculate the dx and the dy. Dx, as we've already said earlier on, the change in x. So for instance, if we have the first point being here, the second point being here, so the change in x, or the dx, so it's going to be our dx, this will be our dy, and if these are the coordinates for the new points that has been given, and if this is it, x1, y1, so this is the coordinate that has been given, so this is our dx, this is our dy, and that will be our dy. So we first of all calculate dx, which is equal to x2 minus x1, and the dy, which is also going to be y2 minus y1. Now the next step is to find the absolute values of dx and also dy. So by finding the absolute value, it's just the same way. The absolute value for dy, so this is dy. We're finding the absolute value, whatever value we get. This is the absolute value symbol. We find the absolute for each of them, and when we have the absolute value for dx, that's of dy, if the absolute value of dx is greater than the absolute value of dy, so in such situations you have m which is less than 1. So m less than 1 takes up the first case which you already have here. So in that case, you have the value of y far lesser than the value of x. So when the absolute value of x is greater than absolute value of y, so in that situation m is less than 1, then k will be represented as the absolute value of x. But the moment the absolute value of x is less than the absolute value of y, then k will be the absolute value of y. So we should have that in mind. So k is equal to the absolute value of x when the absolute value of dx is greater than the absolute value of dy. So the next thing is to create a change in x, which is change in x is to calculate the change in x, which will be equal to dx by the k based on whether m is greater than 1 or m is less than 1, and also the change in y using the value that has been given, the k value that has been given from here, depending on the type of gradient or the type of case that is being used. Now moving on to the next step, which is the initial, the next step, which is step 5. We then initialize the value of the new coordinates, floating coordinates, which is maybe the first one. We then initiate the value of this one. This is the new coordinate to x. So the x value, which is the starting point, is now going to be the new floating point, x coordinate for the floating point, which is x1, and that of y will also be equal to this one. All right. So with that said, then we should also have in mind that once we have initialized the new values of x1 and y1, their respective coordinates, then we can display the points. So the points now becomes xy, which is, so xy here is the new point that we have created using this algorithm. I'm going through this algorithm. And again, the next step, which is step 6, which is what we have done. We have to display this point. So that is this point. Already, this is the point given. Now we've been able to come out with this point. So we have displayed this point. So x now will be equal to x plus the change in x, which is displayed here. And the y value will be equal to y plus the change in y. And again, we also will display the pixel round x. By pixel round x, what we mean to say is, assuming we do the computation for the coordinate x and we get 5 points, maybe 2, we are going to round this 5.2 to 5. And if we get the coordinate for y to be maybe 6.8, we'll round this one to 7. So and display that particular pixel. So what we will be doing is to repeat the step 7 and step 8 k number of times, and mind you, k is the value we got over here. So we'll repeat step 7 and 8 k times to be able to come out with to be able to complete all the points that are needed on all the floating points that are needed on the line, or that are needed to be able to generate the straight line using the DDA algorithm. And of course, the DDA algorithm also has its own disadvantages and also advantages. So first of all, I'm going to talk about the advantages, and also I'll talk about the disadvantages. And the next step would be to come out with an example of this algorithm. So don't really worry, we'll go through a typical example of the algorithm by doing a calculation in an example. Now the DD algorithm has 5 main advantages. And the first one is it is a faster method compared to the direct use of the line equation. So with this comparison, we can see that the DDA algorithm is quite better in terms of speed when we compare with the direct use of the line equation. Now, secondly, it also does not use the multiplication theorem in the DDA algorithm. Now, it's quite impossible, or it's impossible to have the same points plotted twice when you use the DDA algorithm. And the reason is it allows us to detect the change in the value of x and y. Again, another advantage is DDA algorithm gives overflow indication when a point is repositioned. And finally, it is an easy method, mainly because each step involves just 2 addition. It is the step 7 and the 8, as I kept talking about. fact, you will appreciate it when we start with the example that we're going to work through. Now, apart from these, it also has its disadvantages. The first disadvantage that I want us to talk about is that it involves floating points addition. Rounding off is done. This is a problem, and the reason is when we had values of maybe the x-coordinate being 5.2, we rounded it off to 5, and maybe 6.9 to rounded it up to 7, and the accumulation of round off values for these coordinates eventually will cause or will give some sort of accumulated error. So there is a chance of having errors in minimal errors in the plotting of some of the points, the intermediate points that will be used in the generation of the line. Again, the rounding off operation and floating points operation consume lots of time. It sometimes takes a while for you to round off some of the operations and also some of the floating points. And finally, it is more suitable for generating lines whenever you are using a software. It is quite difficult and less suitable for hardware implementation. So when you think of the DDA algorithm, it is best to use this type of algorithm when you are thinking of or considering its usage as a software. But when you think about implementing it in hardware, it's less suitable. So this brings us to the end of the DDA algorithm. So the next slide will be, the next video is going to present on the two examples of how the DDA algorithm works. Thank you.